Hello everyone, and welcome to an example of a cart moving down an incline and using Newton's laws to analyze the motion of said cart. So here's the cart, and as we did in the speeding up and slowing down activity we did earlier this year, we know that if we release a cart from the top of an incline like this, it will accelerate uniformly down the incline. So now our question becomes, what acceleration does it actually have? Can we predict that acceleration? In this case, it's inclined to 21 degrees, which is just the random angle that I made the drawing. Well, the first thing we need to do to find that acceleration is to draw ourselves a force diagram so we can see what's going on. And if you remember, when drawing force diagrams on inclines, we don't leave our axes horizontal and vertical, like they would be normally. We rotate those axes. And notice here, we rotate those axes through the angle theta. Watch it again. That's how much the axes are rotated. And we do that so that the x-axis is parallel to the incline and therefore parallel to the motion. That way, all of the motion of the cart is right along the x-axis. None of the motion is along the y-axis. It makes the motion one-dimensional. It's just that our one dimension is up and down the incline. So, let's continue with the force diagram. We have a force of gravity acting straight down. Since it's not on our new parallel and perpendicular set of axes, we would draw the y component first. That's the part that is perpendicular to the incline. And then we draw the x component, the part that is parallel to the incline. Notice that those are perpendicular components, so notice where the right angle is. Right? It's not over here, it's over here. This x component is parallel to the incline, the y component is perpendicular. And as we just discussed, the angle of inclination, which currently I'm calling theta, is that angle right there, because that's the angle we rotate the axes through. Now there will also be a normal force, a support force if you will, acting on the cart. It will act normal or perpendicular to the surfaces. So notice right along the y-axis, not straight up, right? It's always perpendicular to the surfaces. Now, notice that since we rotated the axes so that all of the acceleration is along the x-axis, there is no acceleration along the y-axis, and therefore the normal force and f of gy must cancel out. That's one of the reasons we make the motion one-dimensional here, so that in the other dimension there is no motion, no acceleration. Since there's no friction, f of gx is left alone here. It's unbalanced. And since f of gx is unbalanced, it will make the cart accelerate. What direction? The same direction it's pointing, which is down the incline. And if we now apply Newton's second law to this situation, we can actually calculate what that acceleration would be. So we're going to use Newton's second law to write an equation for the parallel forces. Newton's second law is net force is mass times acceleration. Now there's only one parallel force, that's f of gx. So that's our net force. So f of gx is equal to ma. Well, we don't know what f of gx is, but we can rewrite it in terms of f of g, the hypotenuse of this right triangle, and the angle theta if we use the sine function. The sine of theta is, of course, opposite side, f of gx, over hypotenuse, f of g. Solve, multiply f of g to both sides, and you get that f of gx can be rewritten as f of g sine theta. And you can substitute that in. Now feel free to skip these steps over here on the side if you can do the trig without writing it out, but here's the steps for you. So we get f of g sine theta equals ma. Now, that doesn't look like it helps us much until we remember that f of g can of course be written as mass times gravitational field strength. Remember, g is not gravity, f of g is gravity or weight. Right, so that's m times gravitational field strength. Plug that in and look at what happens. We now get mg sine theta equals ma. So notice we have a mass over here and a mass over here. Now you may remember from previous discussions that these are fundamentally different masses. The m and the mg is the gravitational mass. The m and the ma is the inertial mass, how much it resists accelerating. However, for reasons which you need general relativity to explain, those are equal to one another. So for all intents and purposes, we can cancel the mass out of the equation. That's kind of cool, because that means that the acceleration doesn't actually depend on the mass of the cart. You could have masses sitting in the cart. You could have an empty cart. It's all going to accelerate the same way. It's only dependent on the gravitational field strength and the angle. So, the acceleration is g sine theta. Plug in what we know. G is, of course, 9.8, and you could write this as newtons per kilogram or meters per second squared, since it's an acceleration we're finding. Sine of 21 degrees, and you get your answer. The cart will accelerate down the incline at 3.5 meters per second squared. That, of course, means every second the cart is speeding up 3.5 meters per second. I hope you've enjoyed this short example of applying Newton's second law to a cart accelerating down an incline.